Greetings everyone. My name is Jayanta. Along with Sapna, both of us will be talking about EpiRust today. So let's briefly understand what this talk is about. From this talk, what all things we can expect. EpiRust is a scientific computing case study. We'll be speaking about building epidemic simulator using a Rust language. We'll be speaking about our journey, about how did we went ahead and built a simulator which is optimized for performance and it can support large scale. Also, we'll be sharing some of our understanding and our insights how Rust as a language helped us building this specific simulator. What is out of scope for the specific talk is we will not be speaking much more detailed about our COVID-19 epidemic model. It deserves its own talk, and this talk is purely going to be technical in nature. But even being said that, we need to cover some of the basic understanding so as to understand the problem statement. And initially in the agenda, we'll specifically talk about EpiRust in the beginning. Then we can talk about memory optimization, performance optimization, results, and the insights which we gathered from this specific tool. That would be towards the end. So let's briefly understand what is an EpiRust. As it has been described, it is an agent-based large-scale open source epidemic simulator. So let's try and understand each and every single term of this. So when we say it's an agent-based simulator, what it means is we understand that spread of a disease is a complex phenomena. All of us have witnessed in past 2 years how COVID-19 is spreading. It is difficult to understand as there are numerous factors which has impact on the spread. So what an agent-based model does is, agent-based model is much more bottom-up approach. Where we start by creating every individual in the society or every individual in the system, which these individuals are of interest for us. So we create every individual person, then we create their homes, then we create their workspaces, and every individual we assign certain schedule to these individuals. So we create a virtual life, virtual society where these individuals are performing their day-to-day routine. They are interconnecting, exchanging some of the information. They are meeting each other in physical world, and all of these interactions can potentially cause a spread of disease. So that is the basic fundamental about agent-based simulation. So on the right, we can see a grid which is depicting a minimalist model which we are using for EpiRust. So every blue dot in this grid is an agent. So this is one of the smaller scale model, which might be for like few hundred individuals. So all of these individuals, they stay in certain home area where they interact with their family members. While going to office, some of these individuals will take space and transport area where they will be accompanied by other individuals who may be strangers. And just by sitting next to each other, there's a chance that a disease can be spread through. So that is why we have a transport section. Similarly, in work area, people will come to work where they will interact with their colleagues. And again, such interactions might lead to spread of disease. And once these individuals come back home, it might happen that someone might get infected at work. And again, the person is in connection with the family members and might spread disease at home as well. So it's a minimalist model which is depicting spread of disease, and in this case specifically COVID-19. So at the bottom it sounds pretty complex, right? But if you want to take this most simple view of EpiRust, I can easily explain it as 2 for loops. So the outer loop is a clock tick. So there is a vector clock which is simulating ours in this context of a virtual society. So what we are doing is at every clock tick, which is at every hour, we are iterating over every agent and asking them to perform their corresponding routine. And once this routine is performed, at the end of each action, we are checking if there is a possibility of spread of a disease. And once we iterate through all the agents, then towards the end, we do stock keeping in terms of we see how many folks got infected in the last hour. Also, if government wants to intervene, if there are certain preconditions which ask government to put a lockdown, which ask government to make to ask people to wear masks or to start a vaccination, such intervention can as well be modeled. So that is most simplified view of EpiRust. So this is our journey. We started very simple. Initially, we started with 1,000 population. Every individual in this case was same as other person. Then slowly we moved to 10,000 individuals and we started bringing heterogeneity. Heterogeneity in terms of ways the individuals go to work. Not everyone in the society is working. There might be younger kids or elders who are staying at home. So based on age, there's stratification. Then there are certain individuals who are essential workers, as in these individuals will still work if there is a lockdown enforced. So we started slowly modeling, capturing the complexity from the domain and making our model rich in terms of domain. The very next target after finishing 10K was to model Pune city, which is a city in India from where both of us are. And since the scale was 3.2 million individuals, scale and performance became the issue pretty quickly for us. Then once we modeled Pune, we went ahead and started modeling Mumbai. So Mumbai is one of the metro cities in India, which has population which is 12 million. So roughly 4 times of Pune. Also, one of the challenges which we faced in the Mumbai context is modeling commute, because many folks in Mumbai, they travel a large distance from one place to reach their workplaces and then come back home. And next goal, which is work in progress, is we want to reach a scale which is 100 million. With 100 million, we can model our state, which is Maharashtra, which is one of the largest state in India, and which as well help us to model multiple cities at the same time. So having said that, let's briefly understand what are technical complexities in this context of EpiRust. EpiRust is compute intensive. So what it means is, if we talk about a simulation which runs for 45 days, the outer loop which we saw for time, it runs for 1080 ticks, because each tick is 1 hour, 45 into 24, which will come down to 1080 ticks. So if we start with a population of 1,000 individuals, so for such a smaller population, there would be 7 million behaviors which needs to be executed in the context of this 45 days. So if we increase population to 1 million, the number from 7 million rises to 7 billion. And moving one step ahead from 1 million to 100 million, the number of behaviors will move on to 700 billion. Also, when we talk about scale, right, if we carefully look at this matrix on the right, the matrix is sparse, that most of the places are empty in this context, which means we will as well need to take care of memory footprint when we are building such a model in memory. And then there are domain complexities. We need to understand what are different things which goes with COVID-19 specifically, because EpiRust is built initially for COVID-19. So we need to understand the way disease works. We need to understand government interventions and how these interventions have impact on individuals' lives. And then adding on to this, there is one more difficulty. So the inner for loop, which we saw earlier, which is per agent, which it executes agent one after the other. But when we speak about agent interactions in real life, all of us move at the same time, and we do not move one after the other. So such a loop causes part dependency. To solve that, we are using 2D buffering algorithm to take care of, to remove the part dependency from the picture. So how did we start? As I said earlier, we started with very simple mechanism. We started with 2 for loops. The code was pretty much serial. The grid which we saw was implemented as 2D matrix. Population for Pune city is 3.2 million, which means if we look at number of cells, this 2D matrix, number of elements this 2D matrix used to hold, that was close to 32 million cells, which means the memory consumption went ahead from, and it was approximately somewhere between 5 to 10 GB, which was pretty big. Keeping our goals in mind, we wanted to model not just for Pune city, but as well as for Mumbai, and want to go ahead and reach the scale with 100 million. So we faced a challenge for modeling the specific grid. One solution which we came up with is, if we can represent this 2D as a grid as a hash map. So we created a structure where the key for hash map is point, and the value becomes object of citizen struct. So point is nothing but XY location on the plane, on the grid, and the citizen is that individual agent who is occupying this specific cell. So essentially what happened is number of agents became number of entries in the specific hash map. Since it is a hash map, retrieval became much more easier. Now instead of order of n square, now it is just plain order of 1 oppositions. Memory, which was earlier in the extent of 5 to 10 GB, right away came to few hundred MBs. We went one step ahead and then we started looking at what can be efficient hashing algorithm which can give us better mileage. So we experimented with hash brown, we experimented with fx hash, we experimented with FNV hash. FNV hash, because it is non-cryptographic and this hash map is not exposed outside. So FNV hash gave us the best possible outcome and we went ahead with FNV hash. Having said that, I'll hand it over to Sapna to talk about how did we optimize for throughput.
Thanks, Jayanta. Now we will be seeing how do we optimize for the throughput performance. So what we tried doing is first implementing the parallel implementation for it. As you saw, we are using 2D buffers. One is the read buffer, from where when our internal for loop starts running, the agent will see its neighboring agent position from the read buffer and update its position according to its daily routine into the write buffer. And each updation of each agent is independent of the other agent status, so we can easily use the data parallelization here. So one of the method was the map reduce, where we actually individually update the agent status and later on serially store it into the temporary some data structure and later on serially update the status in the to the write buffer. That is just to avoid the collision into the map, because we are using buffer as a map. In this case, the parallelization wasn't completely one of the steps we were doing it parallelly and another was a serial. It did give us some performance improvement. Another way was doing is using the parallel iterators, where we use the Rayon library, and what we are doing is using the Rust concurrent data structure dash map, which allows us to atomically do both the stages to check whether the particular entry in the dash map is empty or not, and if it is empty, then you update the agent status there. And as you can see this graph, you can see how we are doing against the 5 million population using the MapReduce or parallel method. If you see the first, where we have throughput 0.5 for the serial implementation, that increases to the double with the MapReduce and almost nearby to it using parallel. But if we go ahead, then the parallel and MapReduce performs same if we go with the higher number of cores, that is 64. That's about the scaling up, where we tried to scale up the population and did the parallel implementation. But another use case we had of the scaling out. As you see, we use the 64 threads and those many CPU cores. If we want to scale it further, we always won't have those many resources available. And from the domain's perspective, sometimes the disease specifications or the geography specifications can be different for the smaller unit of area. One city might have it differently than another city. That's what we did is we segregated those smaller area into the different engines. Each engine will have its own specifications. It will run its simulation, and that way you can run it to the distributed mode, which allows us to use the compute resources efficiently and solves our domain problem as well. Another thing is these engines are not completely isolated from each other. Agents will be traveling from one city to another city or one ward to another ward. In that case, that we are achieving using the Kafka, where data of such commuters is sent over the Kafka and other engines will read it over from Kafka. And this has to be happen at the hour, means if at hour 24 somebody is traveling, it should be reaching at 25th hour or 24th hour depending on the condition, and that for that purpose we have the orchestrator which do nothing but the synchronization of the engines to the particular points. And this is our distributed structure, and we will see how does it help us in optimizing throughput further. So as you see the first graph where we can see the number for the Mumbai and Pune against the serial, parallel and distributed setup, and you can see the for the Mumbai or Pune it actually goes with the serial implementation. When we move to parallel, the throughput has increased to almost twice, and again if we go to the distributed mode, again it's as twice as the parallel implementation. Now that is one way of scaling out. Another way is like as we already saw, the Mumbai has 12 million population, and how did we divide it into the distributed mode is the ward wise distribution, where each engine was having population around half a million, and there were 24 wards. But if we can go little further and reduce the population per engine and increase the number of engines, what we tried with the 100k population each engine, 100 engines, which again sum up to the 10 million, which is near to the 12 million, our throughput actually is the 6 times better as compared to the Mumbai throughput. And that's where the distributed helps us a lot. Now we did changed our engines from 24 to 100, but it is not possible to manually start up the 100 of engines and then start up Kafka and do all of this stuff. We need some sort of scale automation for here and some infrastructure which can be used at this scale. So for that we added the cloud. We migrated to the cloud and added cloud support to our application. First we containerized our EpiRust, and then we used Kubernetes for the container management at the scale. Basically we are using the Kubernetes jobs which runs Kubernetes jobs for the engine and orchestrator, and Kafka is again deployed on the cloud. We are using Helm chart to package the application, so anybody can just according to their use case change the config values in the Helm chart, which way they want to run serial, parallel or distributed, and how many engines, etc. And after the configuration, with single command they will be able to start our application on the cloud and get the output data. Again, if we are having application running at a scale, there are so many issues you need to debug while the developing purpose, or to improve the performance. Most of the metrics are needed. For that we again take advantage of some open source tools like ELK Stack, Prometheus and Grafana for the logging and monitoring purpose, which helped us for debugging, logging and getting some automated alerts. Now we will move to the next part, that is Rust features. So as you know, our basic language is Rust, and all this code, whatever we saw till now, has been written in Rust. And now we will see how Rust helped us to achieve our goal. So as you know already, Rust is closer to the metal, and it gives the performance pretty much similar to the C language. So that helped us a lot. No runtime and no garbage collection, which gives us the quite high performance. But the performance is similar to the C, but C and C++ has many memory issues that we never that Rust is taking care of already, and that's why it saved us quite a lot development time. With the fearless concurrency, we could easily go with the parallel implementation, and most of the errors were coming at the compilation time. Whatever the issues we got later on, there is something related to memory or something related to the language specific. Apart from that, already we saw the performance and memory management helps us in productivity. Overall ecosystem also helped us. The documentation, the way it's written, the various crates for the different use cases, and the cargo as the build tool with its simplicity, all of us helps in the productivity. Most of the features converting it to the parallel using the Rayon library, multi-threading using Tokyo, etc. All of us helps us. Yeah, this is the team which worked on the EpiRust. Thank you. That's it.